Good morning, ladies and gentlemen. It's my great honor to be invited here to give a presentation for the 15th International Scientific Conference, CIBv Civil Engineering and Building Services 2020. The title of my presentation today is Pipeline Structure Crack Monitoring by using PZT-based ultrasonic guided waves. This is Professor Shi YAN. I come from School of Civil Engineering, Shenyang Jianzhu University, China. Here is the outlines of my presentation, which is divided into 5 parts: motivation and methodology, finite element analysis based on upgas, pipeline crack monitoring experiments using PZT-based guided waves. Finally, I would like to give some discussions and conclusions. Here is part 1, motivation and methodology, pipeline damages and their results. As we know, pipelines are widely used for oil and gas transportation. However, pipeline leakage accidents still occur in the world. The external impacts, material initial defects, environmental corrosion, internal erosion, ground surface movements, and improper maintenance may lead to pipeline damages such as cracks. So, early detection of pipeline cracks is of great importance and becomes an important application field for structural health monitoring technologies. Therefore, smart materials such as piezoceramics can be used in pipeline structure health monitoring, PSHM. Piezoceramic transducer-based guided wave technology with advantages of long-range and accurate detection is receiving increasing attention in pipeline structure health monitorings. Figure 1 shows the pipelines widely applied in the world, and Figure 2 is the damaged pipelines. Figure 3 is the ship pollution caused by pipeline leakage, and Figure 4 is typical pipeline damages. In this presentation, we will focus on the crack monitoring of the pipeline using PZT-based guided waves. Piezoelectric materials and piezoelectric effects. Piezoelectric material such as lead zirconia titanate, PZT, is a kind of typical smart material which has famous piezoelectric effects. The positive piezoelectric effect can be used to manufacture sensors, and the inverse piezoelectric effect can be applied to produce actuators. So, PZT transducers are commonly used in structural health monitoring with features of strong piezoelectric effects, quick response, wide frequency band, low cost, and capacity of both actuating and sensing. PZT-based guided waves play an important role in pipeline structural health monitoring and damage detection. Figure 5 shows lead zirconia titanic PZT patches, which will be used in this research. This slide is showing the schematic of piezoelectric effects. Figure 6 is the positive piezoelectric effects, which can be used to produce sensors. When we apply a force on the surface of the PZT patch, the electricity will be generated. I like to take this as an example. A PZT patch is placed on the surface of a cantilever beam. When we apply force here, the electricity will be generated. When we change the direction of the force, the direction of the electricity will be changed again. This is the positive piezoelectric effect. And Figure 7 is the inverse piezoelectric effect, which can be used to produce actuators. when we apply an electric field on the surface of the PZT patch, a movement will be generated. So this is the inverse piezoelectric effect. This is the vibration mode for the piezoelectric vibrators. In this presentation, we will use the thickness vibration mode. Therefore, PZT transducers can be used to generate and receive the guided waves. Figure 9 is the schematic of a guided wave propagation in a pipeline. This is the thickness of a pipe, and this is the direction of the pipe. And there are three typical vibration modes for the guided wave. The first is longitudinal mode, L mode. The second is torsional mode, T mode. And the third is a flexural mode, F mode. And figure 10 is the example of the guided wave propagation mode in a pipeline. This is the L02 mode, and this is F11 mode, and this is the T02 mode. In this presentation, we will use L02 mode. This is the quick review of guided wave in pipeline structural health monitoring. And the key point is how to determine the frequency dispersion and the multiple mode properties of guided waves. A guided wave has typical properties of both frequency dispersions and multiple modes. Appropriate selection of the specific guided waves modes and a suitable frequency range will make the damage detection and structural health monitoring relatively easier. The frequency dispersion and multiple modes properties of an ultrasonic guided wave can be illustrated by velocity dispersion curves. Figure 12 and 13 are frequency dispersion curves of a steel pipe which with an outside diameter of 17 millimeters and wall thickness of 4 millimeters. From figure 12, we can see that L02 mode is very special because of two issues. One, L02 mode, the velocity is the fastest one, which can be detected easily. We can use the head wave method to detect this mode. Second, the dispersion curve is weak, which means the velocity has a small change in the range from 40 kHz to 100 kHz. Therefore, L02 mode with the central frequency of 70 kHz is used in this paper. An excitation signal with the central frequency of 70 kHz and the amplitude of 5 volts is used. Figure 14 is the normalized waveform in time domain, and this is the corresponding wave in the frequency domain. And here is the central frequency of 70 kHz. And this is the establishment of a finished element model. Table 1 is the dimension parameters of the piezoceramic elements. The length of the PZT patch is 12 millimeters, and width is 6 millimeters, and thickness is 1 millimeter. Table 2 is the dimension parameters of a steel pipe model. The length of the pipe is 2 meters, and outside diameter is 70 millimeters, and the wall thickness is 4 millimeter. And table 3 is the mechanical property parameters of steel material. This is the density, this is the Young's modulus, and this is the Poisson's ratio. And table 4 is the mechanical and electrical parameters of PZT materials. And this is dielectric constants. and this is the elastic constant, and this is the piezoelectric constant, and this is the density of the PZT material. To generate an L02 mode guided wave for identifying the circumferential crack, a group of 16 piezoceramic elements simulating the PZT patches array used as actuators are uniformly arranged along the pipe model, and another group of 4 piezoceramic elements used as sensors are uniformly bonded on the surface of the model at the same end. The distance between the generator array and the sensor array is 50 millimeters. The pipe FEA model assembled with the PZT array and the sensor is shown in Fig 16. And here is the actuation end, and this is the reception end. 16 PZT patches are placed here as generators to generate the guided wave. The guided wave mode is L02, and here 4 PZT patches are used as sensors to receive the guided wave. The grid size and maximum time increment are very important during the establishment of the FEA model. The grid size, which should be less than 1/20th of the maximum wavelength, is suggested. The maximum time increment should be less than 1/20th of the period of the excitation signal corresponding to the high-rate frequency. In order to verify whether the excitation signal is approximate to the expected guided wave with an L02 mode in the pipe direction simulation, 3 kinds of typical displacements along axial, radial, and circumferential directions at the given nodes are analyzed, respectively. Firstly, the axial, radial, and the circumferential displacement curves are extracted and compared, as shown in Figure 7 and 17 and 18. Figure 18 shows the actual displacement amplitudes of the signal package at the same nodes in the pipe mode are greater than the other 2 direction ones, which indicates that the displacement distribution approximately compiles with the L-mode guided wave. Secondly, by calculating the time difference between the initial received signal wave package and the echo signal wave 1, the propagation time of the guided waves in the pipe can be calculated. According to the position of the nodes in the pipe, the propagation group velocities of the guided waves in the pipe can be obtained. Table 1 is the result. There are 3 observation points, and here is the propagation times for the first point, the second point, and the third point. This is the calculated group velocities, and this is the theoretical group velocity. It can be observed that the calculated group velocities value are basically as the same as the theoretical value of L02 mode guided wave at the central frequency of the 70 kHz. It is indirectly verified that the excitation signal in this simulation has approximate properties of L02 mode guided wave. As the detection signal propagating along the pipe and reflecting at the ends, the echo signal usually becomes more complicated. By analyzing the displacement time history at given nodes for the healthy pipe, it is found that the initial sensing signal and the echo one at the end have a phenomenon of a waveform superposition and signal package time with the broadening. It is preliminarily speculated that the superposition of the sensing signal occurs at areas near the ends, and the signal package time width broadening comes from the frequency dispersion in the propagation process. In order to clearly explain the phenomenon, the displacement time history response at the nodes with distances away from the excitation ends of 0, 1 meter, 2 meters, and are extracted and analyzed respectively. Through the displacements compared at different nodes, it can be concluded that the incidence wave and boundary reflection ones will occur superposition phenomenon in the closed-end area. In order to determine the superposition area range, a new observation point of a signal wavelength away from the left end is selected. The node displacement of the initial sensing signal and its reflected signal starts clearly separating. From figure 20, we can see that here is initial reception signal, and here is a boundary reflection signal. We can pay attention here, there is a clear waveform separation from the left end, and this is the separation from the right end. Here is the new layout of the transducers and the schematic of signal propagation in the pipe in the simulation. And the distance from the end to the PZT actuators is 20 millimeters, and the distance from the PZT actuators to the PZT sensors is 300 millimeters. And here is the sensing signal time history of a healthy pipe and the new piezoceramic element layout stream in the simulation. We can clearly see there are 4 packages, and this is initial reception signal. It means the wave propagation from here to here, and this is the boundary reflection signal, and this is the echo signal, and the last one is the boundary reflection signal. Therefore, we can clearly understand the meaning of each wave package. This is the simulation analysis of the pipe with circumferential cracks. And this figure is the cross-section of circumferential crack with the radius angle of 45 degrees. And here is the cross-section, and there is an artificial crack here. And the depth of the crack is 3 millimeters, and the width is 2 millimeters, and the thickness of the pipe is 4 millimeters. And this is the schematic of signal propagation in the pipe with circumferential crack in the simulation. And these are PZT actuators, and these are sensors, and there is an artificial crack here. And this is pipe model meshing with circumferential crack of a radius angle of 45 degrees, and here is the crack, and the grid size is 5 millimeters. And here is the sensing voltage signal in the simulation for the pipe with a 45 degrees of circumferential crack. We can pay attention to here. Here is the damaged echo signal, and this package denotes the boundary reflection signal. So this is very important because this package contains the information of cracks. We change the crack dimensions, and the angle of the crack is changed from 45 degrees to 90 degrees, and keep the other parameters unchanged. This is the simulation results. We find that the amplitude of the damaged echo signal package for the 90 degree is greater than that for the 45 degree. This is because the greater size of a crack provides much more energy of the echo signal. Therefore, the echo signal energy can be used as a variable to detect the dimension of the crack. We change the position of a crack to know if the distance can influence the detection. We change the crack from the position 1 meter away from the left end to the 1.5 meter away, and we find that the damaged echo signal moved towards the far end. Therefore, we try to use the shift of the wave package to determine the location of the crack by using the time of flight method. This is part 3, pipeline crack monitor experiment using PZT-based guided waves. We'll focus on experimental setup, the healthy state pipe experiment and result analysis, and the circumferential crack pipe experiment and result analysis. This is the experimental setup. A pipe structural health monitoring test platform was established, aiming at validating the proposed FEA model and numerical simulation results. A function arbitrary waveform generator enabled to output 5 types of basic waveforms. A digital oscilloscope was used as the signal acquisition device in this experiment. 2 groups of PZT patches and an experimental pipe was also applied. A computer was used for data processing and analysis. Firstly, we did the healthy state pipe experiment and result analysis. The healthy pipe was used as a reference for comparing with the damaged results. The result of healthy pipe experiment is similar with the simulation result, and the sensor voltage signal has 2 main wave packages before 1.5 milliseconds. Compared with the initial reception signal, the boundary reflection signal has smaller amplitude due to the signal energy attenuation and a wider time duration because of the frequency dispersion effect. But the energy attenuation in the experiment is a little higher than in the simulation. The signal superposition and the signal time duration broadening phenomenon for the experimentally received signal are more obvious because of a more complex environment for the experiment than for the numerical simulation. 2 kinds of artificial circumferential cracks with a radius angle of 45 degree and 90 degree were used in the experiment respectively. The L02 mode 5-peak wave with a central frequency of 70 kHz and the amplitude of 5 volts modulated by the Henry-Reynolds function was chosen as detection signal in the experiment. This is the sensing signal for the pipe with circumferential crack of 90 degree in the experiment. This is the time history of the signal, and this package is the initial reception signal, and this is the second boundary reflection signal. Between these 2 packages, there are several small packages, and this one is very important, which is the damage echo signal of L02 mode, and the others are the conversion signal. And this is the schematic of the mode conversion signal propagation in the pipe in the experiment. To verify the correctness of the pipe damage detection based on piezoceramic element in the numerical simulation, the sensing experimental signal was compared with the sensing simulated ones. The figure shows a good agreement between the experimental and the numerical result. 3 signal packages represent initial sensing signal, damage echo signal, and boundary reflection signal, and they match well in both amplitudes and phases. However, due to the complex environmental condition, the experimental data have obvious noise, which makes the signal response greater than the simulation one among main signal packages. This is part 2, discussions. To quantificationally describe the damage identification level, a signal energy-based evaluation algorithm is proposed. The entire energy of sensing signal can be expressed as sum of square of value at each time steps, shown in this equation, where xi is discretized signal data and Ej is the energy of sensing signal. To compare the difference for varied signals to clearly represent properties of sensing signals, a dimensionless variable is defined as evaluation index, shown in this equation. Here, alpha n is the evaluation index, representing the relative energy of the sensing signal. N is the number representing the corresponding load level. En here is the signal energy at the corresponding damage levels, and E0 is the excitation signal energy at the healthy state. Table 6 is comparison of signal package amplitudes. There are 3 damage cases. The first case is healthy, the second case is a 45-degree damage, the third case is a 90-degree damage. The first row represents the simulation result, and the second row represents the experimental result. We can find that the absolute error between these two values are very small. Table 7 is comparison of the evaluation index. We can find the absolute errors between these two values are also very small. And table 8 is comparison of the damage localization, and the relative errors is small. So the proposed variable and damage detection algorithm are effective to evaluate the dimensions and locations of the cracks by using PZT-based guided waves. The last part is conclusion. And the FEA model, considering the couple effects of pipe structures and piezoceramic patches, is established and analyzed for crack identification and monitoring in which piezoelectric elements are directly used. The efficiency of the established model and numerical results are validated by the experiment. An FEA meshing method and guided wave selection rules are proposed also. The grid size, which should be less than 1/20th of the minimum wavelength, is suggested. A PCT transducer measurement rule is put forward in which the PCT transducer arrays are suggested to be placed at positions a length of a guided wave away from connections to prevent sensing signal from superposition. The advantage of the rule is validated by both numerical and experimental results. The L02 mode guided wave is suggested to be used in pipe structure damage identification with circumferential cracks. The detection signal frequency can be selected based on the corresponding group velocity dispersion curves, in which the part with maximum grid velocity and weak frequency dispersion are suggested. A PCT guided wave-based experiment system for pipe structure damage identifications is proposed and validated. The damage in the pipe structure can cause and aggravate mode conservation of equal signal. A signal energy-based identification algorithm is proposed. The algorithm is successfully validated by both the numerical simulation and experimental results. Thank you for your attention.